So here's something worth thinking about as you settle in tonight. Right now, at this exact moment, you are moving. Not in some poetic, metaphorical sense. I mean, you are physically hurtling through space at a speed that would be genuinely terrifying if you could feel it. The Earth beneath you is spinning on its axis at roughly 1,000 miles per hour if you're near the equator. And while it's doing that, it's also orbiting the sun at about 67,000 miles per hour. And the sun itself is dragging everything, you, the Earth, all the planets, around the center of the Milky Way at something like 500,000 miles per hour. You are on the fastest ride that has ever existed, and it feels like absolutely nothing. You're lying still. Maybe you've got a blanket pulled up. Maybe the room is quiet. And yet the machinery of the solar system is churning away all around you at speeds that make a jet engine look like it's standing still. That's what we're going to talk about tonight. How all of this works. The whole solar system, the planets, the moons, the orbits, the tides, the seasons, the rings of Saturn, the volcanoes on Jupiter's moons, the reason Pluto got demoted, the asteroid belt, comets, all of it. We're going to take it slow, and we're going to take it from the very beginning. Not the beginning of textbooks, but the beginning of the story, how human beings first started looking up and trying to make sense of what they saw. Because that's really where this starts, right? Long before anyone knew what a planet actually was, people noticed that certain lights in the sky didn't behave like the others. Most stars, thousands of them, moved together across the sky in a slow, predictable rotation, rising and setting like the sun and moon. They kept their positions relative to each other, night after night, century after century. You could draw patterns in them, constellations, and those patterns held. Orion looked like Orion whether you were watching from Babylon or Egypt or the coast of China. The stars were fixed, reliable, almost boring in their consistency. But then there were these other ones, 5 of them, visible to the naked eye, that wandered. They drifted slowly against the background of fixed stars, sometimes moving one direction for weeks, then appearing to stop, reverse course, loop backward, and then continue forward again. The ancient Greeks had a word for them, planets, which just means wanderers, and that's where we get the word planet. These 5 wanderers, Mercury, Venus, Mars, Jupiter, and Saturn, were the only planets anyone knew about for thousands of years. Along with the sun and the moon, they made up the 7 classical celestial bodies. And if that number sounds familiar, it should. That's why we have 7 days in the week. Sunday for the sun, Monday for the moon, Saturday for Saturn. The others are a bit more hidden in English but obvious in Romance languages. Mardi for Mars, Mercredi for Mercury, Jeudi for Jupiter, Vendredi for Venus. The solar system is literally embedded in your calendar. Now, the big question that haunted ancient astronomers, and I mean haunted, this wasn't idle curiosity, this was the deepest intellectual puzzle of the ancient world, was how to explain the motion of these wanderers, because the motion was weird. Mars, for example, would spend most of its time drifting slowly eastward relative to the stars, but then every couple of years it would appear to slow down, stop, and move westward for a few weeks before resuming its eastward path. This is called retrograde motion, and it's one of those things that seems like a minor observational curiosity, but actually drove the entire history of astronomy for 2,000 years. Here's the thing about retrograde motion. If you assume, as almost everyone in the ancient world did, that the Earth is sitting still at the center of everything, and all the planets and stars revolve around it, then retrograde motion makes no sense. Why would Mars suddenly decide to go backward? What mechanism could cause that? The ancient Greek astronomer Claudius Ptolemy, working in Alexandria around 150 AD, came up with an incredibly clever solution. He said that the planets don't just orbit the Earth in simple circles. Instead, each planet moves in a small circle called an epicycle, and the center of that epicycle itself moves in a larger circle around the Earth. So the planet is basically doing a loop-the-loop as it goes around, and when the planet is on the part of its little loop that happens to carry it backward relative to Earth, you see retrograde motion. And you know what? It worked. Ptolemy's system, laid out in his masterwork, the Almagest, was an engineering triumph in its own way. He tuned the sizes and speeds of these epicycles until his model could predict where the planets would be in the sky with remarkable accuracy. Not perfect accuracy. There were always small errors that needed patching with additional adjustments, extra epicycles on top of epicycles, slight offsets and tilts. But good enough to be useful for navigation, for agriculture, for religious calendars. Good enough that it stood as the dominant model of the cosmos for nearly 1,400 years. Think about that. 14 centuries. That's longer than the entire period from Columbus to today, and then some. Ptolemy's geocentric model wasn't just accepted, it was woven into philosophy, theology, and everyday life. The idea that Earth was the center of everything felt right. It matched daily experience. You don't feel like you're moving after all. The sun really does look like it goes around you. But here's what's really interesting about Ptolemy's system. It was accurate enough to be useful, but it was wrong. And the difference between those two things, between a model that works and a model that's true, is one of the most important ideas in all of science and engineering. You can build a system that gives you the right answers for the wrong reasons, and it might serve you well for centuries. But eventually, the errors accumulate, the patches get unwieldy, and someone comes along and says, "Wait, what if we've been looking at this from the wrong angle entirely?" That someone, of course, was Nicholas Copernicus, and his story is fascinating partly because of how cautious he was. Copernicus was born in 1473 in Royal Prussia, modern-day Poland, and he was, by training, a canon lawyer and physician. Astronomy was more of a serious side interest. But sometime in the early 1500s, he began developing an idea that would eventually reshape everything. What if the Earth wasn't at the center? What if the sun was at the center, and the Earth was just another planet orbiting around it? Now, Copernicus wasn't the first person to suggest this. Aristarchus of Samos had proposed a sun-centered model way back around 270 BC, almost 2,000 years earlier. But Aristarchus's idea hadn't gained traction, partly because it contradicted common sense, partly because the observational tools of his time couldn't confirm it, and partly because the philosophical weight of Earth-centered thinking was just too heavy. Copernicus, though, had better mathematical tools, and he worked out a detailed system showing that if you put the sun at the center and let Earth orbit it along with the other planets, retrograde motion suddenly had a beautifully simple explanation. Think about it this way. Imagine you're in a car on a highway, and you're passing a slower car in the next lane. As you pull alongside and then ahead of it, that slower car appears to drift backward relative to the distant landscape behind it, even though it's still moving forward. That's essentially what's happening with Mars. Earth, being closer to the sun, orbits faster than Mars does. So roughly every 2 years, Earth catches up to Mars and passes it. During that passing, Mars appears to move backward against the distant stars. No epicycles needed. No loop-the-loops. just two planets moving at different speeds on different tracks around the same center. It's elegant, it's simple, and Copernicus knew it was dangerous. He circulated his ideas privately for years, sharing a brief summary called the Commentariolus with trusted colleagues around 1514, but he held off on publishing his full work, De Revolutionibus, until 1543, the year he died. Legend has it that a copy of the printed book was placed in his hands on his deathbed. Whether that's exactly true or slightly embellished, the timing tells you something about how nervous he was. And honestly, his caution was partly justified, not because the church immediately condemned him. That's actually a common misconception. The real ecclesiastical trouble came later, but because his system still had problems. Copernicus kept using perfect circles for the orbits, and because planetary orbits aren't actually perfect circles, he still needed some epicycles of his own to make the numbers work. His model was simpler than Ptolemy's, but it wasn't dramatically more accurate in its predictions. It was more of a philosophical shift than a practical one, at least at first. The practical revolution, the moment when the heliocentric model went from being an interesting idea to being obviously, undeniably correct, required two more people, and their stories intertwine in one of the most remarkable collaborations in the history of science. The first was Tycho Brahe, a Danish nobleman born in 1546, who was, by any measure, one of the most extraordinary characters in the history of astronomy. Tycho was flamboyant, wealthy, brilliant, and famously lost part of his nose in a sword duel with a cousin over a mathematical disagreement. He wore a prosthetic made of brass, or possibly gold and silver, for the rest of his life. He kept a pet moose that reportedly died after drinking too much beer and falling down the stairs at a party. I'm not making that up. This was a real person. But here's the thing about Tycho that actually matters. He was the greatest naked-eye astronomical observer who ever lived. Working from his observatory on the island of Hven, given to him by the King of Denmark, Tycho spent over 20 years meticulously recording the positions of the planets with a precision that nobody had achieved before. His instruments were enormous, great brass quadrants and armillary spheres, some of them nearly 20 feet across. And he developed techniques for minimizing observational errors that were genuinely ahead of their time. His catalog of planetary positions, especially his observations of Mars, were accurate to about 1 arc-minute, that's 1/60th of a degree, roughly the limit of what the human eye can resolve. Before Tycho, the best observations had errors of 10 or 15 arc-minutes. He improved the precision by an order of magnitude. And yet, Tycho himself never figured out the correct model of the solar system. He proposed his own compromise, the Tychonic system, where the sun and moon orbited the Earth, but all the other planets orbited the sun. It was mathematically equivalent to the Copernican system in many ways, but it kept the Earth stationary, which Tycho preferred for both physical and philosophical reasons. He couldn't feel the Earth moving, and he couldn't detect stellar parallax, the tiny apparent shift in star positions that should occur if Earth is orbiting the sun. The stars, it turns out, are just so absurdly far away that the parallax is too small to see without a telescope. But Tycho didn't know that. He just knew he couldn't measure it, and he was too good an observer to ignore what his data was telling him. What Tycho needed was someone who could take his magnificent data and extract the truth from it mathematically. And in 1600, near the end of his life, he found that person. A young, impoverished, nearsighted German mathematician named Johannes Kepler arrived at Tycho's new observatory near Prague, and the two began an uneasy collaboration. Tycho was protective of his data, It represented his life's work, and he doled it out to Kepler sparingly, worried that the younger man might use it to prove Copernicus right and render Tycho's own model obsolete, which is, of course, exactly what happened. Tycho died unexpectedly in 1601. The cause of death is still debated, possibly a burst bladder from refusing to leave a banquet to relieve himself, possibly mercury poisoning, possibly something else entirely. And Kepler inherited the treasure trove of observations. What Kepler did with that data over the next decade changed everything, and it started with Mars. Tycho's observations of Mars were the most detailed, and Mars has a noticeably elliptical orbit, which made it the perfect test case. Kepler tried for years to fit Mars's orbit to a circle. He tried combinations of circles. He tried Ptolemaic epicycles. He tried offsets and equants. Nothing worked. There was always an error of about 8 arc-minutes, tiny by historical standards, but Kepler knew Tycho's data was accurate to 1 arc-minute, so 8 arc-minutes of error was unacceptable. Those 8 arc-minutes, Kepler later wrote, were enough to lead to a complete reformation of astronomy, and he meant it. Because those 8 stubborn arc-minutes forced Kepler to do something nobody had been willing to do in 2,000 years of astronomy. He abandoned the circle. Now think about what a radical step that was. Since Plato, since before Aristotle, the circle had been considered the only shape worthy of the heavens. Perfect, eternal, divine. Every astronomer for over 2 millennia, Ptolemy, Copernicus, even Tycho, had assumed that celestial motion must be circular. It was less a scientific conclusion and more a philosophical axiom, something so deeply embedded in how people thought about the cosmos that questioning it felt almost heretical. And here was Kepler, this stubborn, brilliant, half-blind mathematician living on a meager salary in Prague, saying no. The data says otherwise. The planets don't move in circles. But if not circles, then what? Kepler didn't jump straight to ellipses. That's not how discovery usually works. He tried ovals first, egg shapes, various elongated curves. He spent months on calculations that led nowhere, filling page after page with arithmetic done entirely by hand. No calculators, no computers, just Kepler and his pen and Tycho's numbers, and an almost inhuman patience for grinding through long division. At one point he tried a particular oval shape and found that it almost worked, but not quite. And then, and this is one of those moments in the history of science that feels almost too perfect, he realized that the shape he needed was one that mathematicians had understood since ancient Greece, an ellipse. A very specific kind of curve where there are 2 focal points, and the sum of the distances from any point on the curve to those 2 foci is always the same. If you've ever stuck 2 pins in a piece of cardboard, looped a string around them, and traced a curve with a pencil keeping the string taut, you've drawn an ellipse. The 2 pins are the foci. And here's what Kepler discovered. Mars orbits the Sun in an ellipse, with the Sun not at the center of that ellipse, but at one of the 2 foci. That's his first law, published in 1609 in a book called Astronomia Nova, New Astronomy. Planets move in elliptical orbits with the Sun at one focus. It sounds simple when you say it like that. It's one sentence. But it demolished 2,000 years of celestial geometry, and it fit Tycho's data perfectly. Those 8 arc-minutes of error vanished. Now the ellipses of planetary orbits are not wildly elongated. Earth's orbit, for instance, is very nearly circular. The difference between its closest approach to the Sun and its farthest distance is only about 3%. If I drew Earth's orbit on a piece of paper, you'd have trouble telling it apart from a circle. Mars is a bit more eccentric, which is why it was the right planet for Kepler to crack the problem with. But even Mars's orbit looks pretty close to circular. The point isn't that the orbits are dramatically oval. The point is that they're not perfect circles, and that tiny deviation from perfection is what makes the math actually work. Kepler's second law came from the same investigation, and it's just as beautiful. He noticed that Mars doesn't move at constant speed along its orbit. When it's closer to the Sun, it moves faster. When it's farther away, it slows down. But the relationship isn't random. It follows a precise rule. If you draw an imaginary line from the Sun to the planet, that line sweeps out equal areas in equal times. So, in a given month, whether the planet is close to the Sun and moving quickly or far from the Sun and moving slowly, the area of the wedge-shaped region swept out by that line is the same. It's called the equal areas law, and it's a gorgeous piece of geometry. It means there's a deep connection between a planet's distance from the Sun and how fast it's traveling, a connection that would later turn out to be a consequence of the conservation of angular momentum, though Kepler didn't know that yet. He just knew the pattern was there in the numbers. These two laws, elliptical orbits and equal areas, were published together in 1609. The third law took another decade. Kepler published it in 1619 in a book called Harmonices Mundi, the harmony of the world, and it connects different planets to each other. It says that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. So if you know how far a planet is from the Sun, you can calculate how long its year is, and vice versa. Jupiter, for example, is about 5 times farther from the Sun than Earth is. 5 cubed is 125. The square root of 125 is about 11.2. And sure enough, Jupiter's orbital period is about 11.9 Earth years. It's not exact because we're rounding, but the law holds beautifully across all the planets. What's remarkable about Kepler's 3 laws is that they're purely descriptive. They tell you what the planets do, but not why. Kepler himself spent enormous energy trying to figure out the why. He had this idea that the Sun exerted some kind of force that pushed the planets along, something like magnetism. He'd read William Gilbert's work on magnets and was deeply influenced by it. He imagined a kind of sweeping force radiating from the Sun, rotating with it, pushing planets through space. It was wrong in the details, but the intuition was extraordinary. He was groping toward gravity decades before anyone formalized it. And speaking of gravity, this is where we need to talk about someone else who was working on motion around the same time, though in a very different way. While Kepler was up in Prague wrestling with planetary orbits, down in Italy, Galileo Galilei was pointing a telescope at the sky for the first time and fundamentally changing what humans knew about the cosmos. Galileo didn't invent the telescope. That was probably Hans Lippershey, a Dutch spectacle maker, around 1608. But Galileo heard about it, built his own improved version, and had the inspired idea to point it upward. What he saw was staggering. The moon wasn't a perfect smooth sphere as Aristotle had taught. It had mountains and craters and valleys, rough and irregular, a world with geography. Jupiter had 4 moons of its own, actual satellites orbiting another planet, proof that not everything in the universe orbited Earth. Venus went through a full set of phases, just like our moon, which only made sense if Venus was orbiting the Sun, not Earth. The Milky Way, that hazy band of light, resolved into countless individual stars, too faint to see with the naked eye. Galileo published these observations in 1610 in a slim book called Sidereus Nuncius, the Starry Messenger. and it was a sensation. It didn't prove the Copernican model outright, but it demolished several key pillars of the old Aristotelian worldview. The heavens were not perfect and unchanging. Earth was not the only center of orbital motion, and there were far more stars than anyone had imagined, which hinted at a universe vastly larger than the cozy Ptolemaic cosmos. Now, Galileo's story gets tangled up with the Catholic Church in ways that are often oversimplified. The standard version, brave scientist persecuted by ignorant religious authorities, has some truth to it, but the real story is more complicated and, honestly, more interesting. Galileo had powerful supporters within the Church, including cardinals and even the Pope himself for a while. The problem wasn't just that heliocentrism contradicted certain biblical passages, though it did. The problem was also political, personal, and temperamental. Galileo was brilliant, but also combative and sometimes arrogant. He had a talent for making enemies. When he published his dialogue concerning the two chief world systems in 1632, he put the Pope's own arguments into the mouth of a character named Simplicio, literally the simpleton, and that did not go over well. His trial and house arrest in 1633 were a tragedy for science, but they didn't stop the heliocentric model from spreading. By that point, the evidence was too strong. But here's what Galileo contributed that goes beyond telescopic observations. He fundamentally changed how people thought about motion itself. Through careful experiments, rolling balls down inclined planes, studying pendulums, thinking deeply about falling objects, he established principles that would become the foundation of classical mechanics. He showed that objects in motion tend to stay in motion unless something stops them, which is the seed of what we now call inertia. He showed that the acceleration due to gravity is the same for all objects, regardless of their weight, at least in the absence of air resistance. He separated the study of motion into horizontal and vertical components that could be analyzed independently. These ideas might sound basic now, but they were revolutionary. Aristotle had taught that objects naturally come to rest, that heavier things fall faster, that motion requires a continuous force. Galileo overturned all of that through experiment and reasoning, and in doing so, he created the toolkit that the next generation would need to finally answer the question Kepler couldn't. Why do the planets move the way they do? That next generation arrived in the form of a man born on Christmas Day, 1642. The same year Galileo died, as if the universe had a sense of narrative timing. Isaac Newton came into the world premature and tiny, in a small manor house in Lincolnshire, England. His father had died before he was born. His mother remarried when he was 3 and left him with his grandmother. By all accounts, he had a difficult childhood, and he grew into a difficult adult, secretive, vindictive, prone to long feuds, and possessed of perhaps the most powerful scientific mind in human history. Newton's contributions to our understanding of the solar system are so foundational that it's hard to know where to start. But let's begin with the story everyone knows, or thinks they know. The apple. There's actually some truth to it. Newton himself told the story late in life, and his friend William Stukeley recorded it. In 1666, during the plague years when Cambridge University was closed and Newton had retreated to his family's farm, he saw an apple fall from a tree and began thinking about whether the force that pulled the apple to the ground might be the same force that kept the moon in its orbit around Earth. The same force, just reaching out across all that empty space between here and there. That's the thought that changed everything. Not immediately, mind you. Newton was careful, almost pathologically so, about publishing his ideas. But the seed was planted right there, in that quiet Lincolnshire garden, during a plague year when the world had slowed down enough for one extraordinary mind to think very, very deeply. So let's follow that thought, because it's one of the most beautiful chains of reasoning in the history of science. Newton asked himself, if the force of gravity reaches up to the moon, does it follow the same rules as it does here on the ground? And if so, can I prove it mathematically? Here's how he approached it. He knew from Galileo's work that an object in free fall near Earth's surface accelerates at a specific rate, roughly 32 feet per second squared, or about 9.8 meters per second squared if you prefer metric. He also knew, roughly, the distance from the Earth to the moon, about 60 Earth radii, give or take, and he knew how long the moon takes to complete one orbit, about 27.3 days. Now, here's where it gets clever. If the moon is traveling in a roughly circular path around the Earth, then it's constantly being deflected from a straight line. Remember Galileo's insight about inertia. An object in motion stays in motion in a straight line unless a force acts on it. The moon wants to fly off in a straight line, but something keeps bending its path into a curve. That something, Newton proposed, is gravity. The same gravity that pulls apples down. And the amount the moon falls toward Earth each second, the amount it deviates from a straight line path, can be calculated from its orbital speed and distance. So Newton did the calculation. He figured out how far the moon falls toward Earth in 1 second due to the curvature of its orbit. Then he compared that to how far an apple falls in 1 second at Earth's surface. And here's the thing. If gravity diminishes with the square of the distance, meaning if you double the distance, the force drops to a quarter, triple the distance, it drops to a ninth, and so on, then the moon, being about 60 times farther from Earth's center than the apple, should experience a gravitational acceleration that's 1 over 60 squared, or 1/3600th of what the apple feels, and it matched. Not perfectly. Newton's first attempt in 1666 was a bit off because the accepted value for Earth's radius wasn't quite right at the time, and that bothered him enough to shelve the whole project for years. But the basic proportionality was there. The moon really does fall toward Earth at almost exactly the rate you'd predict if gravity follows an inverse square law. The same force, the same rule, just weaker with distance. That's the moment when heaven and earth became one system. Not poetically, not philosophically, mathematically. But Newton didn't publish any of this in 1666. He sat on it. For nearly 20 years, he sat on it. He went back to Cambridge, became a professor, did groundbreaking work on optics and light, invented calculus, or co-invented it, depending on which side of the Newton-Leibniz feud you come down on, and that feud was vicious, one of the ugliest in scientific history, with accusations of plagiarism flying in both directions and the Royal Society essentially being weaponized as a tribunal. But that's a story for another time. The point is, Newton had the key insight about gravity in his 20s and didn't share it with the world until he was in his 40s. What finally pushed him was a conversation in 1684 with Edmund Halley. Yes, the comet guy, though the comet wouldn't be named after him until later. Halley visited Newton in Cambridge and asked him a question that had been stumping the best minds in London. If gravity follows an inverse square law, what shape would a planet's orbit be? Newton answered immediately, an ellipse. Halley was stunned and asked how he knew. Newton said he'd calculated it years ago. Halley asked to see the proof. Newton rummaged around, couldn't find it, and promised to redo it and send it along. What Newton sent was far more than a proof. It was the beginning of the Principia, the Philosophia Naturalis Principia Mathematica, published in 1687, arguably the most important scientific book ever written. And Halley, bless him, not only encouraged Newton to write it, but personally financed its publication, because the Royal Society had blown its budget on a lavish history of fish that didn't sell very well. So the foundational text of modern physics exists in part because of an unsold fish book. You can't make this stuff up. The Principia laid out Newton's 3 laws of motion, which you probably remember in some form. First, an object at rest stays at rest, and an object in motion stays in motion in a straight line unless acted on by a force. That's inertia, formalized from Galileo's insight. Second, force equals mass times acceleration. Simple, elegant, and extraordinarily powerful. Third, for every action, there's an equal and opposite reaction. These 3 laws, combined with his law of universal gravitation, gave humanity the ability to predict the motion of essentially everything: cannonballs, pendulums, tides, moons, planets, comets. And let's talk about that law of universal gravitation specifically, because it deserves to be savored. Newton proposed that every object in the universe with mass attracts every other object with mass. The force between them is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Think about what that means. You, right now, lying there, are gravitationally attracting every object in your room: your phone, your pillow, the walls, and they're attracting you. The forces are absurdly tiny because your masses are small compared to, say, a planet, but they're real. They're measurable. Gravity isn't something that only planets do. It's something everything does. It's woven into the fabric of having mass at all. Now, here's where Newton's framework becomes breathtaking in its explanatory power. Remember Kepler's 3 laws? Elliptical orbits, equal areas in equal times, the period-distance relationship? Kepler discovered them empirically. He found the patterns in Tycho's data, but he couldn't explain why they were true. Newton derived all 3 of Kepler's laws from first principles. They fell out of his equations like mathematical consequences. If gravity follows an inverse square law and objects obey Newton's laws of motion, then orbits must be ellipses. The equal area law must hold. The relationship between period and distance must follow exactly the pattern Kepler found. Kepler's laws went from being mysterious observations to being inevitable outcomes of deeper physics. That's unification. That's what physics is supposed to do: take seemingly separate phenomena and reveal them as expressions of the same underlying truth. And Newton didn't stop with planets. He tackled the tides, showing that they result from the gravitational pull of the moon and the sun on Earth's oceans. He explained the precession of the equinoxes, that slow wobble of Earth's axis that takes about 26,000 years to complete a full cycle, showing it was caused by the gravitational tugging of the moon and sun on Earth's equatorial bulge. He analyzed the orbits of comets, demonstrating that they too obeyed the same gravitational laws, just on highly elongated elliptical paths. The solar system, in Newton's framework, became a vast clockwork, every motion predictable, every trajectory calculable, if you knew the masses and the starting conditions. This is worth sitting with for a moment. Before Newton, the solar system was a collection of observed patterns. After Newton, it was a machine whose behavior could be predicted with stunning precision. You could calculate where Jupiter would be 100 years from now. You could predict when a comet would return. You could figure out how much a distant planet's gravity would tug on a nearer one and account for that perturbation in your calculations. The universe became, in a very real sense, knowable. And people tested it. They tested it relentlessly, and it kept working. Halley used Newton's methods to calculate the orbits of several comets and noticed that the comets of 1531, 1607, and 1682 had remarkably similar orbital elements. He proposed they were the same comet, returning every 75 or 76 years, and predicted it would return again around 1758. Halley died in 1742, but on Christmas night, 1758, a German farmer and amateur astronomer named Johann Georg Pallich spotted the comet exactly where Newton's physics said it should be. It was named Halley's Comet, and its return was one of the most powerful confirmations of Newtonian mechanics the world had ever seen. A man had used mathematics to predict the future, and the universe had obliged. But here's the thing about Newtonian mechanics. It's so good that when it seems to fail, the failure itself becomes a discovery. And that's exactly what happened with the planet Uranus. Uranus was discovered in 1781 by William Herschel, a German-born musician living in England who had taken up astronomy as a hobby and built his own telescopes. Really good ones, better than most professionals had. He spotted a faint object that moved against the background stars and initially thought it was a comet, but its orbit turned out to be nearly circular, far beyond Saturn. It was a new planet, the first discovered in recorded history, and it doubled the known size of the solar system overnight. Astronomers tracked Uranus carefully over the following decades, calculating its predicted orbit using Newton's laws and accounting for the gravitational influence of Jupiter and Saturn. But Uranus kept drifting off course. Not by much, tiny discrepancies, fractions of an arc-minute, but they accumulated. By the 1840s, the deviations were undeniable. Something was pulling on Uranus, something that wasn't in the calculations. Now, there were two possibilities. Either Newton's law of gravity was wrong at very large distances, or there was another planet out there, one nobody had seen yet, tugging on Uranus with its gravity. Two mathematicians, working independently, bet on the second option. John Couch Adams in England and Urbain Le Verrier in France both calculated where this hypothetical planet would need to be to produce the observed perturbations in Uranus's orbit. Le Verrier sent his predictions to Johann Galle at the Berlin Observatory, and on September 23, 1846, Galle pointed his telescope at the coordinates Le Verrier specified and found Neptune within 1 degree of the predicted position, on his very first night of looking. 1 degree. That's twice the width of a full moon. From pure mathematics and Newton's laws, they told an astronomer where to point his telescope, and there was a planet waiting. Think about what that means for a second. They discovered a world, an entire world, not by seeing it, but by noticing its gravitational fingerprint on another planet's motion and then calculating backward to find the source. That's the power of Newton's framework, and it set the stage for an even more dramatic search, one that would take decades longer and lead to a result nobody expected, involving a planet that turned out not to be a planet at all, the story of Vulcan. And it's one of the strangest detours in the history of astronomy, because it shows you what happens when a theory works so spectacularly well that people trust it even when it's leading them astray. See, after the triumph of Neptune's discovery, astronomers were riding high on Newtonian gravity, and rightfully so. The method had worked beautifully. Find an anomaly, assume there's an unseen mass causing it, calculate where that mass should be, point a telescope, and there it is. So when another orbital anomaly showed up, the instinct was obvious. Do it again. And the anomaly in question involved Mercury, the smallest, fastest, closest planet to the Sun. Mercury's orbit is an ellipse, like all the planets, and the point where it comes closest to the Sun, its perihelion, shifts slightly with each orbit. This is called the precession of the perihelion. Now, some of that precession is expected. Jupiter, Venus, Earth, all the other planets tug on Mercury a little bit, and those tugs cause the perihelion to rotate slowly around the Sun over time. Newtonian mechanics predicts this beautifully for every planet, except Mercury. When Leverrier, the same Leverrier who'd nailed Neptune, sat down and carefully calculated all the known gravitational influences on Mercury, he found that the predicted precession came up short. There was an extra 43 arcseconds per century that couldn't be accounted for. 43 arcseconds per century. That's an incredibly tiny amount. We're talking about a discrepancy so small that it would take Mercury's perihelion about 3 million years to make one full extra rotation around the Sun beyond what Newton predicted. But Leverrier was meticulous, and the discrepancy was real, and it wouldn't go away no matter how carefully he redid the math. So what did he do? Exactly what had worked before. He proposed that there must be an undiscovered planet, or perhaps a belt of small bodies, orbiting closer to the Sun than Mercury, and their gravitational pull was causing the extra precession. He even gave this hypothetical planet a name, Vulcan, after the Roman god of fire and the forge. Fitting, right? A planet so close to the Sun it would practically be sitting in the forge itself. And here's where it gets fascinating, because people actually claim to see it. In 1859, a French amateur astronomer named Edmond Modeste Lescarbot reported observing a small dark body transiting across the face of the Sun. Leverrier visited him, interrogated him about his observations, and became convinced this was Vulcan. Leverrier announced the discovery, and for a while, it seemed like he'd done it again. Found another planet through the sheer power of mathematical prediction. He was awarded honors. Newspapers reported the discovery. The astronomical community buzzed with excitement. But other astronomers couldn't confirm it. During solar eclipses, which would be the best time to spot a planet very close to the Sun, since the Sun's glare would be blocked, search after search came up empty. Some observers reported sightings, but they were inconsistent with each other. The objects they claimed to see were in different places, had different sizes, moved at different speeds. None of it held together. And as telescopes improved and solar observation techniques got better through the 1860s, 1870s, 1880s, no credible, repeatable observation of Vulcan ever materialized. Leverrier died in 1877, still believing Vulcan existed. He went to his grave convinced that the method that had given him his greatest triumph, the discovery of Neptune, would eventually vindicate him again. But it never did, because Vulcan wasn't there. The anomaly was real, but the explanation was wrong, and the true explanation wouldn't come for almost another 40 years. And when it did, it would require abandoning the very framework that had made the prediction possible in the first place. Let that sit for a moment. Newton's laws, which had worked flawlessly for over 2 centuries, which had predicted Neptune's position to within a degree, which governed everything from cannonballs to comets, those laws had a blind spot. And that blind spot was hiding right there in Mercury's orbit, 43 arcseconds per century, waiting patiently for someone to come along with a better theory. That someone, of course, was Albert Einstein. And the theory was general relativity, published in November 1915. Now, Einstein's path to general relativity is one of those stories that deserves some space because it wasn't a sudden flash of insight. It was a decade-long struggle, arguably the most intense sustained intellectual effort any single human being has ever undertaken. Einstein had published Special Relativity in 1905, which dealt with objects moving at constant velocities relative to each other and gave us the famous relationship between energy and mass. But special relativity had a problem. It didn't include gravity. It worked beautifully in the absence of gravitational fields, but the moment you tried to incorporate gravity, the framework broke down. And Einstein knew this. It bothered him. The key insight came from what Einstein later called the happiest thought of his life. Imagine you're standing in an elevator, or a lift, depending on where you're from, and the cable snaps. You're in free fall. During those terrifying seconds, you would feel weightless. You'd float inside the elevator, just like an astronaut in orbit. A ball you released from your hand would hover in front of you. For all practical purposes, inside that falling elevator, gravity has vanished. Einstein realized that this meant something profound. Gravitational acceleration and the acceleration you feel when you're pushed back into your seat in an accelerating car are fundamentally the same thing. You cannot tell them apart with any local experiment. This is the equivalence principle, and it became the foundation stone of general relativity. But getting from that insight to a complete mathematical theory took Einstein from roughly 1907 to 1915, and it nearly broke him. He had to learn entirely new branches of mathematics, Riemannian geometry, tensor calculus, subjects that were deeply abstract and that most physicists of his era had never touched. He made wrong turns. He published preliminary versions that had errors. He collaborated with his friend Marcel Grossmann, who was a mathematician, and together they got tantalizingly close in 1913, but couldn't quite close the gap. Einstein spent months going down blind alleys, sometimes thinking he'd solved it, then finding mistakes. By the fall of 1915, he was in a race, partly against himself, partly against the great mathematician David Hilbert, who was also working on gravitational field equations using similar mathematical tools. In November 1915, Einstein presented his completed field equations to the Prussian Academy of Sciences in a series of 4 Thursday lectures. And during that month, as he was finalizing the theory, he did something that must have sent chills down his spine. He used his new equations to calculate the precession of Mercury's perihelion, and out popped 43 arc-seconds per century, exactly the amount that had been unexplained since Leverrier first identified the discrepancy 60 years earlier. No fudge factors, no adjustable parameters, no hypothetical hidden planet. The geometry of space-time itself, curved by the sun's mass, produced precisely the right correction to Mercury's orbit. Einstein later told a friend that when he saw the result, he felt heart palpitations. He said he was beside himself with joy for days, and you can understand why. This wasn't just a successful prediction. It was a confirmation that his entire conceptual revolution was on the right track. Gravity wasn't a force pulling objects through space, the way Newton had described it. Gravity was the curvature of space-time caused by mass and energy, and objects moved along the straightest possible paths through that curved geometry. Mercury, being the closest planet to the Sun, and therefore deep in the Sun's gravitational well, where space-time is most strongly curved, showed the effect most prominently. The other planets experienced it too, but the effect was much smaller, and within the margin of observational error at the time. So here's the thing about this moment in the history of our understanding of the solar system. Newton wasn't wrong, exactly. His theory is an extraordinarily good approximation. For nearly every practical purpose, launching satellites, calculating eclipses, planning space missions, Newtonian gravity works perfectly. General relativity only becomes necessary in situations involving very strong gravitational fields, very high velocities, or very precise measurements. Mercury's perihelion precession happens to be one of those situations where the difference matters, because Mercury moves fast, sits close to a massive object, and we can measure its orbit with extraordinary precision over long periods of time. But the conceptual shift is enormous. In Newton's universe, gravity is a force that acts instantaneously across empty space. The sun pulls on Earth, and Earth pulls on the sun, and somehow this influence travels across 93 million miles in zero time. Newton himself was uncomfortable with this. He wrote that the idea of gravity acting at a distance without any intervening medium was, in his words, so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew something was missing from his own theory. He just couldn't figure out what. Einstein's answer was that gravity doesn't act at a distance at all. Instead, mass and energy warp the fabric of space-time, and that warping propagates at the speed of light. The sun doesn't reach out and grab Earth. The sun's mass creates a curved region of space-time around it, and Earth follows the natural contours of that curvature. It's like, imagine placing a heavy bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, the marble curves toward the bowling ball, not because the bowling ball is pulling it, but because the sheet itself is curved. That analogy isn't perfect. Space-time curvature is four-dimensional and involves time as well as space, but it gives you the flavor of the idea. And this reframing changes how we think about orbits entirely. When you picture Earth going around the sun, you might imagine it being constantly pulled inward, like a ball on a string. But in Einstein's picture, Earth is actually following the straightest possible path through curved space-time. It's moving in what's called a geodesic. From Earth's own perspective, it's going straight. It's space-time itself that's curved, and that curvature is what we experience as gravity. The planets aren't being pulled. They're following the shape of the universe around them. Now, general relativity also made predictions that went far beyond explaining Mercury. Einstein predicted that light itself would be bent by gravity, that a beam of light passing close to the sun would be deflected by the sun's mass. This was tested during a total solar eclipse on May 29, 1919, when the British astronomer Arthur Eddington led expeditions to the island of Principe off the west coast of Africa and to Sobral in Brazil. They photographed stars near the sun during totality and compared their apparent positions to where those stars appeared when the sun was elsewhere in the sky. The results matched Einstein's prediction, not Newton's, and the announcement made Einstein an overnight global celebrity. Headlines around the world declared that Newton had been overthrown, which was an oversimplification but made for great newspapers, and general relativity predicted something else, something that connects directly to how the solar system works on the most fundamental level. It predicted that time itself runs differently depending on where you are in a gravitational field. A clock sitting on the surface of the sun would tick slightly slower than a clock floating far out in empty space, because the sun's gravity warps not just space, but time. This is called gravitational time dilation, and it's not some exotic theoretical curiosity. It's something we have to account for every single day in the GPS satellites orbiting Earth. Those satellites carry atomic clocks, and because they're higher up in Earth's gravitational field, farther from Earth's center, their clocks tick slightly faster than clocks on the ground. The difference is tiny, about 45 microseconds per day faster due to the gravitational effect, partially offset by a slowing of about 7 microseconds per day due to their orbital velocity. That's the special relativistic time dilation. If we didn't correct for both of these effects, GPS positions would drift by roughly 10 kilometers per day. So every time you use your phone to navigate to a restaurant, you're relying on Einstein's corrections to Newton's gravity. The solar system taught us that lesson through Mercury's stubborn little orbit. But here's what's really lovely about this whole story. Einstein didn't make Newton obsolete. He extended him. Newton's laws are contained within general relativity as a special case, the case where gravity is relatively weak and speeds are much less than the speed of light, which describes almost everything in our everyday experience and most of what happens in the solar system. You can plan a mission to Mars using nothing but Newton, and you'll get there just fine. But if you want to understand the universe at its deepest level, if you want to know why Mercury's orbit does that tiny extra wobble, if you want to understand black holes or gravitational waves or the expansion of the universe itself, you need Einstein. And speaking of understanding the solar system at a deeper level, there's another question that Newton's framework raised but couldn't fully answer, one that people had been wondering about for centuries before him, and that wouldn't get a satisfying resolution until the 20th century. The question is deceptively simple. Where did the solar system come from? How did you get a star with a family of planets orbiting in nearly the same plane, nearly the same direction, with rocky ones close in and gas giants farther out? What process could produce something so orderly from the chaos of space? Because when you look up at the night sky, if you really think about it, there's no obvious reason why a bunch of gas and dust should organize itself into a neat little system with a glowing ball in the center and a handful of worlds circling around it like clockwork. And yet, here we are. The first person to take a serious crack at this was someone you've already met in a different context, Immanuel Kant. Yes, the philosopher. In 1755, Kant proposed what he called the nebular hypothesis. His idea was that the solar system began as a vast, diffuse cloud of gas and particles, slowly rotating, and that over time this cloud collapsed under its own gravity, flattening into a disk, with the densest part collecting at the center to form the sun and the remaining material clumping together to form the planets. For a philosopher working decades before anyone had the mathematical tools to really test this, it was a remarkably good guess. And independently, about 40 years later, the French mathematician Pierre-Simon Laplace arrived at essentially the same picture. Laplace gave it more mathematical rigor, proposing that as the rotating cloud contracted, it would spin faster. Conservation of angular momentum, the same reason an ice skater spins faster when they pull their arms in. And that rings of material would be shed from the outer edge of the contracting cloud, each ring eventually condensing into a planet. This became known as the Kant-Laplace nebular hypothesis, and for a long time, it was the leading idea. But here's the thing, it had problems, serious ones. The biggest was something called the angular momentum problem. If the solar system really formed from a single collapsing, spinning cloud, you'd expect most of the angular momentum, the rotational oomph, if you like, to be concentrated in the biggest, most massive object, the sun. But that's not what we observe. The sun contains about 99.8% of the mass of the entire solar system, yet it carries less than 2% of the total angular momentum. Jupiter alone, despite being 1,000 times less massive than the sun, carries the lion's share of the angular momentum. That's weird. That's like a figure skater pulling her arms in and spinning incredibly slowly, while her discarded gloves somehow spin faster than she ever did. It didn't make sense, and for a long time, nobody could explain it. So alternative theories cropped up. One of the more dramatic ones was the tidal hypothesis, championed in the early 20th century by James Jeans and Harold Jeffreys. Their idea was that a passing star came close enough to the sun to pull out a long filament of hot gas through tidal forces, kind of like how the moon raises tides on Earth, but much more violent. This filament would then condense into planets. It was a vivid image, and it neatly sidestepped the angular momentum problem because the angular momentum would come from the encounter itself, not from the sun's rotation. But it had its own issues. For one thing, the mathematics showed that hot gas pulled from the sun would simply disperse into space rather than condense into planets. It would be far too hot and diffuse to clump together. For another, close stellar encounters are extraordinarily rare, especially in our part of the galaxy. If planet formation required such a fluke event, then planetary systems would be vanishingly uncommon in the universe. We now know that's not the case. Planets are everywhere. But even at the time, the tidal hypothesis felt unsatisfying to a lot of people. So for a while, the origin of the solar system was genuinely up for grabs. You had competing ideas, none of them fully convincing, and the whole question sort of languished in a frustrating limbo through the first half of the 20th century. What changed everything was a return to the nebular hypothesis, but with new physics. Starting in the mid-20th century, people like Viktor Safronov in the Soviet Union and later researchers in the West began working out the detailed mechanics of how a collapsing cloud of gas and dust would actually behave. And the key insight that resolved the angular momentum problem turned out to involve something beautifully mundane: friction, or more precisely, magnetic braking and turbulent viscosity within the disk. Here's how it works. Picture that collapsing cloud of gas, what astronomers call a molecular cloud. These are real things you can observe. The Orion Nebula, for instance, is a stellar nursery where new stars are forming right now, about 1,300 light-years from Earth. When a region within such a cloud becomes dense enough, its own gravity overwhelms the internal pressure holding it up, and it begins to collapse. As it contracts, it spins faster, just as Laplace said. And because the cloud has even a tiny bit of initial rotation, which it always will, because nothing in the universe is perfectly still, conservation of angular momentum means the spin rate increases as the radius shrinks. Material falling inward along the rotation axis can fall freely toward the center, but material in the plane of rotation gets caught up in the spin and can't fall straight in. It settles into an orbiting disk, so you naturally get a flattened structure, a protoplanetary disk, surrounding a growing central mass, the protostar. Now, the angular momentum problem. The young sun should be spinning much faster than it actually does. What slows it down? The answer involves the sun's magnetic field interacting with the ionized gas in the inner disk. The magnetic field lines act almost like elastic bands connecting the young star to the surrounding material. As the star tries to spin faster, those magnetic field lines transfer angular momentum outward from the star to the disk. It's like spinning on an office chair while holding a rope attached to a heavy weight on the floor. The rope pulls back on you, slows your spin, and tugs the weight. Over millions of years, this magnetic braking efficiently moves angular momentum from the central star outward into the disk, and from there into the forming planets. That's why Jupiter ended up with so much angular momentum and the Sun ended up with so little. The physics actually works beautifully once you include magnetism and the detailed behavior of ionized gas. And this is where the story of planet formation itself gets really fascinating, because the disk doesn't just sit there, it evolves. Close to the young Sun, temperatures are scorching, thousands of degrees. Only materials with very high melting points can exist as solids there. We're talking metals and silicate minerals, rocky stuff. Farther out from the Sun, beyond a boundary that astronomers call the frost line or snow line, it's cold enough for volatile compounds like water, ammonia, and methane to freeze into solid ice crystals. And this distinction, this temperature gradient across the disk, is the fundamental reason why the inner solar system has small rocky planets and the outer solar system has giant planets rich in hydrogen and helium. Think about it this way. In the inner disk, the only solid building blocks available are grains of rock and metal. These are relatively rare compared to the light gases like hydrogen and helium that make up the bulk of the cloud. So the solid particles that can form in the inner disk are limited in quantity. They collide, stick together, grow from microscopic dust grains into pebbles, then boulders, then kilometer-sized bodies called planetesimals. This process, accretion, is slow and produces relatively small rocky worlds. Mercury, Venus, Earth, Mars. None of them is even close to the mass of Jupiter. But beyond the frost line, you've got all that rocky and metallic material plus enormous quantities of ice. Water ice, carbon dioxide ice, ammonia ice. The total mass of solid material available is maybe 3 to 4 times greater than in the inner disk. So out there, planetesimals can grow much bigger, much faster. And here's the critical threshold. Once a solid core reaches roughly 10 Earth masses, and this number comes from detailed models first worked out by people like Safronoff and later refined by researchers like Peter Goldreich and Scott Tremaine. Once you hit that mass, the core's gravity becomes strong enough to start pulling in the surrounding hydrogen and helium gas directly from the disk. And hydrogen and helium are by far the most abundant elements. So the planet doesn't just grow, it undergoes what's called runaway gas accretion. It balloons. In maybe just a few 100,000 years, it goes from a 10 Earth mass rocky icy core to a behemoth hundreds of times the mass of Earth, wrapped in a vast atmosphere of hydrogen and helium. That's Jupiter. That's Saturn. It's a gorgeous explanation because it emerges naturally from basic physics, gravity, temperature, and the composition of the original cloud. You don't need to invoke anything exotic. The same disk, the same process, just different temperatures at different distances, and you get 2 fundamentally different kinds of planet. Now, Uranus and Neptune are interesting because they're sort of in between. They're much bigger than Earth, but much smaller than Jupiter and Saturn. They have thick atmospheres of hydrogen and helium, but they're mostly made of ices and rock. The leading idea is that they formed farther out where the disk was thinner and the orbital timescales were longer, so they grew their solid cores more slowly. By the time their cores got big enough to start capturing gas, the disk was already dissipating. The sun's radiation and solar wind were blowing the remaining gas away. So they grabbed some gas, but not nearly as much as Jupiter and Saturn did. They're sometimes called ice giants to distinguish them from the gas giants, and that name really does capture what makes them different. But here's where the story takes an unexpected turn, because the nice, neat picture of planets forming in place and staying put, rocky ones here, gas giants there, everything in its proper lane, turns out to be too simple. Starting in the mid-1990s, a series of discoveries forced astronomers to completely rethink how planetary systems evolve after they form. And the trigger wasn't even something in our own solar system. It was the discovery of the first exoplanets, planets orbiting other stars. In 1995, Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in southern France, announced the detection of a planet orbiting the sun-like star 51 Pegasi. And the planet was bizarre. It was roughly the mass of Jupiter, but it orbited its star in just 4 days. 4 days. That put it incredibly close to the star, much closer than Mercury is to our sun. A Jupiter-mass planet in an orbit where surface temperatures would exceed 1,000 degrees. They called these things hot Jupiters, and nobody had predicted them. Nobody thought a gas giant could exist that close to a star, because there simply isn't enough solid material in the inner disk to build a 10 Earth mass core and trigger runaway gas accretion. So how did it get there? The answer, almost certainly, is that it didn't form there. It formed farther out, beyond the frost line, just like our Jupiter, and then it migrated inward. And this idea, planetary migration, changed everything. It turns out that a young planet embedded in a gas disk doesn't just orbit quietly. It interacts gravitationally with the disk, creating spiral density waves, and those waves exert torques back on the planet. Depending on the details, those torques can push the planet inward or outward, sometimes dramatically. A Jupiter-mass planet can spiral from 5 astronomical units all the way down to a fraction of an astronomical unit in less than 1,000,000 years. That's terrifyingly fast on astronomical timescales, and it raised an obvious and slightly unsettling question about our own solar system. Did our planets migrate too? Did Jupiter start somewhere else and move to where it is now? And the answer, as best we can tell, is yes. Almost certainly yes. And the story of how we figured that out is one of the most creative pieces of detective work in modern planetary science. So let's talk about it. Let's talk about what's called the NICE model. And that's NICE as in the city in France, N-I-C-E, because it was developed by a group of researchers working at the Observatoire de la Côte d'Azur, which is in Nice. It was first published around 2005, primarily by Rodney Gomes, Hal Levison, Alessandro Morbidelli, and Cleomenes Tsiganis. And what they proposed was, frankly, a little wild. They said that the outer solar system used to look completely different from how it looks today. That the giant planets, Jupiter, Saturn, Uranus, and Neptune, were all originally packed much more tightly together, all orbiting between roughly 5 and maybe 15 astronomical units from the Sun. That's a much more compact arrangement than what we see now, where Neptune is out at 30 astronomical units. And beyond these tightly packed giants they proposed, there was a massive disk of leftover icy planetesimals, billions of small rocky icy bodies stretching out to maybe 30 or 35 astronomical units, just sitting there, quietly, for hundreds of millions of years. And then something happened. Here's the thing about gravitational interactions between planets. They're subtle, but they accumulate. Jupiter and Saturn, orbiting relatively close to each other, were slowly exchanging angular momentum with the outer planetesimal disk. Every time a small, icy body drifted inward and had a gravitational encounter with Neptune, or Uranus, or Saturn, it would get flung somewhere, maybe inward, maybe outward, and in the process, the planet that flung it would recoil slightly in the opposite direction. This is just Newton's third law playing out on a planetary scale. Over millions of years, These countless tiny interactions caused the orbits to drift. Neptune drifted outward, Uranus drifted outward, Saturn drifted outward, and Jupiter, being the most massive and doing most of the flinging, drifted slightly inward. Now, here's where it gets dramatic. At some point, the NICE model suggests this happened roughly 600 to 700 million years after the solar system formed, so around 3.9 billion years ago, Jupiter and Saturn drifted into what's called a mean motion resonance. Specifically, a 2-to-1 resonance, meaning Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. And when 2 massive planets lock into a resonance like that, the gravitational kicks don't average out anymore. They reinforce. They build. It's like pushing a child on a swing. If you push at random times, nothing much happens. But if you push at exactly the right moment in each swing, the amplitude grows and grows. That's what happened. The resonance between Jupiter and Saturn pumped up their orbital eccentricities, and the gravitational disturbance cascaded outward to Uranus and Neptune. And the result was chaos. Genuine, mathematical chaos. The orbits of Uranus and Neptune became unstable. In many of the computer simulations, Uranus and Neptune actually swap positions. The one that started closer to the Sun ends up farther out, and vice versa. Neptune gets flung outward into that dense disk of icy planetesimals, and it plows through them like a bowling ball through pins. Billions of small icy bodies get scattered in every direction. Some get thrown inward, toward the inner solar system. Some get thrown outward into extremely distant orbits. Some get ejected from the solar system entirely, flung into interstellar space. And this is the part that made people sit up and pay attention, because it might explain something that had puzzled planetary scientists for decades. There's a period in the history of the inner solar system called the Late Heavy Bombardment. If you look at the surfaces of the Moon, Mercury, Mars, any body that still preserves its ancient craters, there's evidence of an intense spike in impact rates around 3.9 billion years ago. The Moon's large impact basins, the ones we can see with the naked eye as the dark patches on the lunar surface, many of them seem to date to this narrow window. And for years, people wondered, why would there be a sudden surge of impacts hundreds of millions of years after the solar system formed? By that point, the original debris from planet formation should have been mostly swept up. Where did all those impactors come from? The NICE model offered an answer. They came from Neptune's rampage through the outer planetesimal disk. When Neptune was gravitationally scattered outward and plowed through that disk, it sent a rain of icy bodies cascading into the inner solar system. Some of them struck the Moon. Some struck Earth. Some struck Mars and Mercury. The timing fits. The intensity fits. It was a beautiful piece of work, a single dynamical event that explained the current orbital architecture of the outer planets and the late heavy bombardment simultaneously. Now, I should say, the late heavy bombardment itself is actually somewhat debated these days. Some more recent analyses of lunar samples and crater statistics suggest the bombardment might have been less of a sharp spike and more of a gradual tail-off. The evidence is genuinely contested, and the NICE model has been revised and updated multiple times since 2005. There are versions where the instability happens earlier, maybe within the first 100 million years rather than at 700 million years. The core idea, that the giant planets migrated and underwent a period of dynamical instability, that part has held up remarkably well. The exact timing and details are still being refined. But let's think about what this means for a moment. Think about what this picture implies for our solar system's history. Jupiter, the largest planet, the gravitational anchor of the entire system, didn't just form in place and sit there quietly for 4.5 billion years. It migrated. It shifted inward. And in doing so, it may have profoundly shaped the inner solar system. There's actually a related idea called the Grand Tack hypothesis, proposed around 2011 by Kevin Walsh and colleagues. In this scenario, Jupiter didn't just drift a little. It migrated inward through the gas disk early on, during the first few million years when the gas was still present, sweeping all the way into about 1.5 astronomical units from the Sun. That's roughly where Mars is now. And then Saturn, migrating inward behind it, caught up and locked into a resonance with Jupiter, and the gravitational dynamics of that resonance reversed their migration. They both started moving outward again. Jupiter tacked, like a sailboat changing direction. It swept inward, then swept back out. And here's why this matters. As Jupiter swept inward, it would have scattered and depleted the material in the inner disk. It would have pushed rocky debris around, starved certain regions of building material. And when it swept back out, it would have left behind a depleted zone. This might explain one of the persistent puzzles about our solar system: why Mars is so small. Mars has only about 1/10 the mass of Earth, and traditional planet formation models have always struggled to explain why. If there was plenty of rocky material in the inner disk, Mars should have grown bigger. But if Jupiter swept through that region and scattered most of the material away before tacking back outward, then Mars formed from whatever scraps were left. It was starved. It never had a chance to grow. Think about that for a second. The size of Mars, a planet that has captivated human imagination for centuries, a planet we're actively trying to send people to, might be a direct consequence of Jupiter's wandering through the inner solar system 4.5 billion years ago. The architecture of our planetary system isn't some neat, orderly arrangement that fell into place naturally. It's the aftermath of a complicated, chaotic gravitational dance. And this connects to something even broader. When we look at other star systems, and by now we've discovered thousands of exoplanets, thousands of other solar systems, we see an enormous diversity of architectures. Some systems have hot Jupiters. Some have super-Earths, these planets bigger than Earth but smaller than Neptune, packed in tight orbits. And by the way, super-Earths are incredibly common in the galaxy, but our solar system doesn't have one, which is itself a puzzle. Some systems have planets in perfectly resonant chains, where each planet's orbital period is a neat ratio of its neighbors. Some systems look nothing like ours at all. And the reason for all this diversity, we now believe, comes down to migration. Every planetary system forms from a disk. Every disk has slightly different properties: different mass, different temperature profile, different lifetime before the gas dissipates. And the planets that form in those disks interact with them gravitationally, migrate, sometimes gently, sometimes violently. The final arrangement you end up with depends on the details of that migration history. It depends on whether the gas disk dissipated before or after the planets reached a resonance. It depends on whether there was an instability event like the one in the Nice model. Small differences in initial conditions lead to vastly different outcomes. Our solar system, with its orderly inner rocky planets and well-spaced outer giants, might actually be somewhat unusual. We don't know yet. The statistics are still coming in. But there are hints that our particular arrangement, the one that allowed a stable, habitable Earth to persist for billions of years, might require a fairly specific sequence of events. Which brings us to something that connects all of this back to the inner solar system, to the rocky worlds, to the places where the real geological and atmospheric drama plays out. Because once the planets settled into roughly their current orbits, once the migration was done, the instability had passed, and the late heavy bombardment tapered off, the solar system entered a long, relatively stable era. And in that era, the individual personalities of the planets really started to emerge. Mercury, Venus, Earth, Mars, 4 rocky worlds, all born from the same disk, all made of roughly similar stuff, all orbiting the same star. And yet, they turned out completely differently, wildly, dramatically differently. Mercury is a dense, cratered, airless ball of iron. Venus is a hellscape with surface temperatures hot enough to melt lead, wrapped in a crushing carbon dioxide atmosphere 90 times thicker than Earth's. Earth is the one with oceans and life, and a magnetic field and plate tectonics. And Mars is a cold, dry desert with a whisper-thin atmosphere, but with unmistakable evidence that it was once warm and wet. Why? Why did 4 siblings turn out so differently? And the answer involves something we haven't really talked about yet. Atmospheres. How planets get them, how they keep them, and how they lose them. Because the story of a rocky planet's surface conditions is really the story of its atmosphere. And that story starts with where the atmosphere comes from in the first place. And there are really 2 main sources. The first is outgassing, volcanoes. When a rocky planet is young and hot, its interior is churning, convecting, and that volcanic activity releases gases trapped in the rock. Carbon dioxide, water vapor, nitrogen, sulfur compounds, all of that comes belching out of volcanic vents and gradually accumulates above the surface. The second source is delivery from space, comets and volatile-rich asteroids slamming into the young planet, bringing water and other gases with them. Both of these processes were happening on all 4 rocky planets early in the solar system's history. They were all getting atmospheres. They were all accumulating blankets of gas around themselves. But here's the thing. Getting an atmosphere is only half the battle. Keeping one is the real challenge, and whether a planet holds on to its atmosphere depends on a surprisingly simple tug-of-war between 2 forces. On one side, you've got gravity, the planet's mass pulling gas molecules down, holding them close. On the other side, you've got the thermal energy of those gas molecules, their speed, their kinetic energy, their desperate desire to fly off into space. And the outcome of that tug-of-war depends on a few key factors: the planet's mass, its surface temperature, and the mass of the individual gas molecules themselves. Let's think about that for a second. A gas molecule at any given temperature is moving at some average speed. Lighter molecules, hydrogen, helium, move faster than heavier ones like carbon dioxide or nitrogen, because at the same temperature, lighter particles zip around more quickly. That's just basic kinetic theory. Now, every planet has what's called an escape velocity, the speed something needs to reach to break free of the planet's gravity entirely. For Earth, that's about 11 kilometers per second. For Mars, it's only about 5. For tiny Mercury, about 4.3. So the question becomes, are the gas molecules in your atmosphere moving fast enough to escape? If a significant fraction of them are, your atmosphere slowly leaks away into space. It's not dramatic. It's not like a balloon popping. It's more like a slow, patient evaporation happening over millions and billions of years, molecule by molecule, the fastest ones at the tail end of the speed distribution reach escape velocity and drift off, never to return. This is called Jeans escape, named after the British physicist James Jeans, who worked out the mathematics of it in the early 20th century. And it's one of the key reasons the inner planets ended up so different. Mercury, being small and close to the Sun, meaning it's hot and has low gravity, basically couldn't hold on to any atmosphere at all. Whatever gases its volcanoes produced, whatever volatiles got delivered by impacts, they just leaked away. Mercury's escape velocity is low, its dayside temperature is scorching, and the solar wind, that constant stream of charged particles flowing out from the Sun, strips away whatever's left. So Mercury ended up essentially naked. A bare rock with a face full of craters, looking a lot like our moon. Mars had a different problem, but the outcome was similar in some ways. Mars is bigger than Mercury. It's about half the diameter of Earth, so it had a better shot at holding an atmosphere, and early on, it did. There's overwhelming geological evidence that Mars once had a thicker atmosphere, liquid water on its surface, river valleys, lake beds, maybe even a shallow ocean covering much of the northern hemisphere. The Mars rovers and orbiters have found minerals that only form in the presence of liquid water, clays, sulfates, hematite spherules. Something was keeping Mars warm enough for liquid water, and that something was almost certainly a thicker atmosphere providing a greenhouse effect. But Mars lost it, and the reason Mars lost its atmosphere is one of the most important stories in planetary science because it connects to something you might not immediately think of, the planet's magnetic field, or rather, its lack of one. Here's how that works. Earth has a global magnetic field generated by its liquid iron outer core. You know this. It's why compasses work. That flowing, convecting liquid metal creates what's called a dynamo, a self-sustaining magnetic field that wraps around the entire planet like an invisible shield. And that shield does something crucial. It deflects the solar wind. Those charged particles streaming out from the Sun, they hit Earth's magnetosphere and get redirected around the planet, channeled toward the poles where they create the auroras. Beautiful light shows, but more importantly, the magnetic field prevents the solar wind from directly interacting with the upper atmosphere and stripping it away. Mars once had a magnetic field too. We know this because the Mars Global Surveyor spacecraft, which arrived at Mars in 1997, detected strong remnant magnetism in the ancient southern highlands, patches of crust that were magnetized billions of years ago when the planet still had an active dynamo. But at some point, roughly around 3.5 to 4 billion years ago, Mars's dynamo shut down. The core cooled, or the convection stopped, or some combination of factors caused the magnetic field to collapse. And once that shield was gone, the solar wind had direct access to the Martian atmosphere. The MAVEN mission, that's the Mars Atmosphere and Volatile Evolution mission, which NASA put into orbit around Mars in 2014, was designed specifically to study this process. And what MAVEN found confirmed the picture beautifully. The solar wind is actively stripping away Mars's atmosphere right now, today, at a rate of about 100 grams per second. That doesn't sound like much, but over billions of years, it adds up to an enormous amount of lost atmosphere. MAVEN's measurements allowed scientists to extrapolate backward and estimate that Mars has lost the majority of its original atmosphere to space through this solar wind stripping process, combined with other escape mechanisms like sputtering and photochemical escape. So Mars went from a world that might have been habitable, warm, wet, with a reasonably thick atmosphere, to the cold, dry desert we see today. Not because anything catastrophic happened in a single moment, But because of a slow, relentless process spanning billions of years, the magnetic field died, the atmosphere eroded, the surface water evaporated or froze or soaked into the ground, and Mars became the quiet, rusty world we know. It's honestly one of the most poignant stories in the solar system. A planet that had a shot at being something like Earth and lost it. Now, Venus. Venus is the really interesting case, because Venus went wrong in the opposite direction. Venus is almost the same size as Earth. It's sometimes called Earth's twin, though that's deeply misleading once you look at the surface conditions. Venus has plenty of atmosphere. Too much, in fact. Its atmosphere is about 96% carbon dioxide, and it's so thick that the surface pressure is about 92 times Earth's atmospheric pressure. That's equivalent to being almost a kilometer underwater in Earth's oceans. And all that carbon dioxide creates a runaway greenhouse effect that pushes surface temperatures to around 460 degrees Celsius. That's 860 Fahrenheit. Hotter than Mercury, even though Venus is nearly twice as far from the Sun. The greenhouse effect on Venus is so extreme that it completely overwhelms the distance factor. And here's what's fascinating. Venus might have once been habitable too. Climate models published by Michael Way and colleagues at NASA's Goddard Institute for Space Studies in 2016 suggested that Venus could have maintained liquid water oceans on its surface for up to 2 billion years if it had the right initial conditions: a slow rotation rate, the right cloud cover, a modest amount of water. The idea is that early Venus, with a younger, slightly dimmer sun, might have been a perfectly pleasant world. So what happened? Why did Venus become a furnace? The leading theory involves a feedback loop, and it's a terrifying one, honestly, because it has implications for our own planet. At some point, Venus's surface temperature rose enough, perhaps due to increased solar luminosity as the sun gradually brightened over billions of years, or perhaps triggered by massive volcanic resurfacing events, that the oceans began to evaporate. Water vapor is itself a powerful greenhouse gas, so more evaporation meant more greenhouse warming, which meant more evaporation, which meant more warming. A vicious cycle. Eventually, all the water was in the atmosphere as vapor, where ultraviolet radiation from the sun broke the water molecules apart, a process called photodissociation. The lightweight hydrogen atoms escaped to space, and the oxygen either escaped or reacted with surface minerals, so Venus lost its water permanently. And without liquid water, there was no mechanism to pull carbon dioxide out of the atmosphere through the carbonate-silate weathering cycle, the process that on Earth acts as a long-term thermostat, drawing CO2 out of the air and locking it into rocks. On Venus, all the carbon dioxide just accumulated in the atmosphere, with nowhere to go. And this is where the comparison to Earth becomes really illuminating, because Earth has roughly the same total amount of carbon as Venus. The difference is that on Earth, most of that carbon is locked up in carbonate rocks, limestone essentially, on the ocean floor and in the crust. It's not in the atmosphere. If you took all of Earth's carbonate rocks and released their carbon dioxide back into the atmosphere, you'd end up with an atmosphere remarkably similar to Venus's. Same pressure, same composition, roughly. Earth and Venus started with similar inventories of carbon. One kept its water and regulated its carbon cycle. The other didn't. And this brings up something you might already be sensing. The role of liquid water isn't just about biology, about having a nice place for life to evolve. Liquid water is a geological agent. It's part of the planet's thermostat. It enables weathering, which pulls greenhouse gases out of the air. It lubricates plate tectonics. There's strong evidence that water in the mantle helps tectonic plates subduct, and without water, you might not get plate tectonics at all. And plate tectonics itself is part of the carbon cycle, recycling carbonate sediments back into the mantle, where they release CO2 through volcanism, completing the loop. It's an incredibly elegant system when you step back and look at it. Carbon dioxide comes out of volcanoes, warms the planet, gets pulled out of the atmosphere by weathering and dissolved in ocean water, gets deposited as carbonate on the seafloor, gets subducted back into the mantle, and comes out of volcanoes again. A thermostat that's been running on Earth for billions of years. But it's a thermostat that requires certain conditions to function. You need liquid water. You need plate tectonics. You need a magnetic field to protect the atmosphere from solar wind stripping. You need to be at the right distance from your star, in what's often called the habitable zone, or sometimes the Goldilocks zone, the range of orbital distances where surface temperatures allow liquid water to exist. Earth sits comfortably in that zone. Venus is at the inner edge, or possibly just inside it. Mars is at the outer edge, or possibly just outside it. And the boundaries of that zone aren't fixed. They depend on atmospheric composition, cloud cover, planetary albedo, stellar luminosity, and all sorts of factors that make the calculation surprisingly complex. What's remarkable is how narrow the window seems to be. Move Earth just a few % closer to the sun, and models suggest you might trigger a runaway greenhouse. Move it a few % farther out, and you risk a snowball state, the entire planet freezing over, which actually happened to Earth at least twice during the Snowball Earth episodes around 700 million years ago. Earth recovered from those because volcanic CO2 continued to accumulate in the atmosphere even when the weathering cycle was shut down by ice cover, eventually warming things enough to melt the ice. But it was a close thing. The system has tipping points, and Earth has flirted with them more than once. And all of this, the atmospheres, the magnetic fields, the carbon cycles, the water, all of it connects back to the interior of the planet. What's happening deep below the surface determines what happens on top. The size of the iron core determines whether you get a dynamo. The heat budget of the mantle determines whether you get volcanism and plate tectonics. The initial water content determines whether you get oceans. And the planet's mass determines whether you can hold on to an atmosphere in the first place. It's all connected. The surface conditions of a rocky planet are really just the visible expression of processes happening hundreds and thousands of kilometers below. Processes that were set in motion during the planet's formation 4.5 billion years ago and have been playing out ever since. Which brings us to something that ties all of these threads together. Something that's been quietly shaping everything we've talked about, from planetary orbits to atmospheric retention to the possibility of life. And that's the sun itself, because we've been talking about the planets as if the sun is just sitting there, a steady, reliable light source. But the sun has its own story, its own evolution, its own life cycle. And that life cycle has consequences for everything orbiting around it. So let's talk about the sun, not as a backdrop, not as a fixed lamp in the sky, but as a living, changing, aging star. Because the sun you see today is not the sun that shone on the early Earth. And it's definitely not the sun that will shine on the Earth a billion years from now. Here's the first thing that might surprise you. When the solar system was young, 4.5 billion years ago, when those rocky planets were still cooling, still outgassing their first atmospheres. The sun was about 30% dimmer than it is today. 30%. That's enormous. If you took the sun's current output and dialed it down by 30%, the Earth should have been frozen solid. The math is pretty straightforward. With that much less energy arriving at Earth's orbit, the average surface temperature should have been well below freezing. Ice everywhere. No liquid water, no oceans. But we know that's not what happened. We have geological evidence, sedimentary rocks, water-deposited minerals, even chemical signatures of biological activity, going back nearly 4 billion years. The early Earth had liquid water. It had oceans. It was warm enough for life to get started. So how do you reconcile a faint young sun with a warm, wet Earth? This is called the faint young sun paradox, and it was first clearly articulated by Carl Sagan and George Mullen back in 1972. And it's one of those beautiful problems where the answer, or at least the most widely accepted answer, connects right back to everything we were just talking about: atmospheres, greenhouse gases, and the delicate balance of a planet's surface conditions. The most likely explanation is that the early Earth's atmosphere had a much higher concentration of greenhouse gases than it does today. Probably a lot more carbon dioxide, maybe methane too, possibly produced by early microbial life. That thicker greenhouse blanket trapped enough heat to compensate for the weaker sunlight. And then, as the sun gradually brightened over billions of years, the carbonate-silicate weathering cycle we talked about, that beautiful thermostat, slowly drew down the CO2, keeping temperatures roughly stable even as the energy input increased. It's an elegant solution. The planet's climate regulation system was essentially compensating for a changing star, adjusting the atmospheric insulation as the external heat source grew stronger. Think about that for a second. The Earth has been unconsciously, mechanically tracking the sun's output for billions of years, maintaining conditions suitable for liquid water through a feedback loop involving rocks, rain, volcanoes, and ocean chemistry. No one designed it. It just works, as long as the pieces are in place. But here's the thing. The thermostat has limits, and the sun isn't going to stop brightening. The reason the sun gets brighter over time is actually pretty simple, and it has to do with how fusion works in the core. The sun generates energy by fusing hydrogen into helium. 4 hydrogen nuclei combine to form one helium nucleus, releasing energy in the process. That's what's been happening in the core for 4.5 billion years, and it'll keep happening for roughly another 5 billion. But as hydrogen is consumed and helium accumulates in the core composition changes. Helium is denser than hydrogen. As the helium fraction increases, the core contracts slightly under its own gravity, which increases the pressure and temperature at the center. And higher temperature means faster fusion rates. Faster fusion means more energy output. More energy output means a brighter sun. It's gradual, about 1% brighter every 100 million years or so. You'd never notice it in a human lifetime, or even across all of recorded human history. But over geological time, it adds up relentlessly. And it means that in roughly 1 billion years, maybe 1.5 billion, the sun will be bright enough that Earth's thermostat won't be able to keep up. The habitable zone will have shifted outward, just enough that Earth's position becomes problematic. Oceans will start evaporating in earnest. More water vapor in the atmosphere means more greenhouse warming, which means more evaporation. That same runaway feedback loop that destroyed Venus. Earth's long run of habitability, remarkable as it's been, has an expiration date. Not because of anything the planet does wrong, but because the star it orbits is slowly, inexorably changing. Now, that's 1 billion years away, so nobody needs to lose sleep over it tonight. Literally. But it does put things in perspective, doesn't it? The window of habitability for any planet around any star is finite. It opens when conditions are right and closes when the star evolves past the point where those conditions can be maintained. For Earth, that window has been open for about 4 billion years and will probably stay open for another billion or so. 5 billion years total, give or take. That's a long time by any human measure, but it's not forever. And what happens after that billion years? Well, the sun keeps evolving. In about 5 billion years, the hydrogen fuel in the core will be essentially exhausted. At that point, the core, now mostly helium, will contract further, heating up the shell of hydrogen around it enough to ignite hydrogen fusion in that shell. This is a pivotal transition. The energy output increases dramatically, and the outer layers of the sun respond by expanding enormously. The sun will swell into what's called a red giant, growing so large that its outer edge will reach roughly the current orbit of Earth, maybe past it. Mercury and Venus will almost certainly be engulfed. Whether Earth itself gets swallowed or merely scorched to a cinder is actually still debated. It depends on how much mass the sun loses during the red giant phase, which affects the orbital distances of the planets. If the sun loses enough mass, Earth's orbit will spiral outward, potentially staying just ahead of the expanding surface. But even if Earth avoids being physically consumed, it won't matter much for habitability. The oceans will be long gone. The atmosphere will have been stripped or transformed. The surface will be molten or blasted. It'll be a dead world either way. Meanwhile, something interesting happens farther out. As the sun expands and brightens as a red giant, the habitable zone shifts outward dramatically. Mars might briefly become warmer, though it lacks the atmosphere and magnetic field to take advantage of it. But the moons of the outer planets, places like Europa, orbiting Jupiter, or Enceladus and Titan, orbiting Saturn, those could see their icy surfaces melt. Europa already has a subsurface ocean kept liquid by tidal heating from Jupiter's gravity. In a red giant phase, it might have open water on its surface for the first time. Titan, with its thick nitrogen atmosphere and complex organic chemistry, could become genuinely interesting from a habitability standpoint. It's speculative, of course, and the red giant phase doesn't last that long in cosmic terms, maybe 1 billion years. But it's a fascinating thought. The habitable zone is a moving target, and worlds that are frozen wastelands today might have their moment in the warmth eventually. After the red giant phase, the sun will shed its outer layers entirely, puffing them off into space as a beautiful expanding shell of gas, what astronomers call a planetary nebula, which is a terrible name because it has absolutely nothing to do with planets. The term dates back to William Herschel, actually, who thought these fuzzy round objects looked a bit like the disk of a planet through his telescope. The name stuck, even though we now know they're dying stars. Inside that expanding shell, what's left of the sun's core will be exposed, a dense, hot remnant about the size of Earth, but with roughly half the mass of the current sun. A white dwarf. It will glow with residual heat, slowly cooling over billions and billions of years, eventually fading to a cold, dark cinder. A black dwarf, though the universe isn't old enough for any white dwarf to have cooled that far yet. The oldest white dwarfs we know of are still glowing. And the planets? The ones that survive, probably Mars, Jupiter, Saturn, Uranus, Neptune, They'll still be there, orbiting a fading ember. The solar system will persist in a sense, but it'll be a very different place. Dark, cold, quiet. The grand show of planetary atmospheres and magnetic fields and weather systems and geology. All of that will have wound down. The energy source that drove it all will have spent itself. But here's what I want you to sit with, because I think it's the most remarkable thing about everything we've covered tonight. From the very beginning, from that collapsing cloud of gas and dust, from the angular momentum that flattened it into a disk, from the tiny grains of dust that stuck together and grew into planetesimals, from the gravitational sorting that put rocky worlds close to the sun and gas giants farther out. From all of that, what emerged was a system, not a collection of random objects, but an interconnected, dynamic system where everything influences everything else. Jupiter's gravity shaped the asteroid belt and may have determined how much water Earth received. The sun's magnetic field slowed the original nebula's rotation, allowing planets to form in the first place. A planet's distance from the frost line determined its composition, which determined its mass, which determined whether it could hold an atmosphere, which determined its surface conditions, which determined whether liquid water could exist, which determined whether the chemistry of life had a chance to get started. And the people who figured all this out, that's maybe the most human part of the story. It started with ancient observers who just noticed that some lights in the sky moved differently from the others. Wanderers, they called them, planets. And from that simple observation, across thousands of years, through Ptolemy's epicycles and Copernicus's quiet revolution, and Tycho's meticulous measurements, and Kepler's stubborn insistence that the orbits had to be ellipses, through Galileo's telescope, and Newton's falling apple, and Halley's predicted comet, and Herschel's accidental discovery, and Leverrier's mathematical ghost, and Einstein's curved space-time. Through all of that, we built a picture. Not all at once, not without mistakes, not without wrong turns and abandoned theories and decades of confusion. But piece by piece, generation by generation, the picture came together. And it's still coming together. Right now, tonight, there are spacecraft sending back data from the outer solar system. The James Webb Space Telescope is studying the atmospheres of exoplanets, looking for the chemical fingerprints of water vapor and carbon dioxide, trying to figure out if the processes we see in our solar system play out the same way around other stars. The MAVEN orbiter is still circling Mars, measuring how quickly the solar wind strips away what's left of its atmosphere. Missions are being planned to Europa, to Titan, to places where we think liquid water might exist beneath the ice. Every one of those missions is built on the accumulated understanding of centuries, on Kepler's laws to calculate the trajectories, on Newton's gravity to navigate the flybys, on Einstein's relativity to synchronize the clocks. It's all connected. That's the thing that keeps coming back, isn't it? The solar system isn't a collection of separate topics, orbits over here, atmospheres over there, the sun doing its own thing. It's one story, a story about gravity and angular momentum and energy and time, about how a cloud of gas became a star with a family of worlds, each one shaped by the same physics, but expressing it differently depending on where it formed, how big it got, and what happened along the way. And you're part of that story, by the way. The atoms in your body were forged in stars that lived and died before the sun was born. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was cooked up in the cores of massive stars and scattered across space in supernova explosions, billions of years ago. That material ended up in the cloud that collapsed to form our solar system. It ended up in the disk, in the dust grains, in the planetesimals, in the Earth. And eventually, through 4 billion years of chemistry and biology, it ended up in you, lying here, listening to someone talk about how the solar system works, while the very same solar system spins quietly around you in the dark. The planets are out there right now. Jupiter is pulling on its moons with the same gravity Newton described. Saturn's rings are catching sunlight you won't see for another hour or two. Mars is losing 100 grams of atmosphere every second to the solar wind, just as it has been for billions of years. And the sun is fusing hydrogen into helium, getting just a tiny bit brighter, as it has been doing since before there was anyone around to notice. It all just keeps going, quietly, steadily, governed by the same laws that Kepler first glimpsed in Tycho's numbers 400 years ago. And there's something deeply peaceful about that, I think. The solar system doesn't need you to understand it in order to work. But the fact that you can understand it, that a mind made of stardust can look up and figure out why the planets move the way they do, that might be the most extraordinary thing in the whole story. So let that settle over you. Let the orbits turn. Let the sun do its slow, patient work. You don't need to hold on to any of this. It'll all still be there in the morning. For now, just rest. The solar system will keep itself running while you sleep.